start recording the second half of our class, and let me share the screen. Okay, in this topic is the normal and tangential coordinate. Before this, the first coordinate that we review and we use it to analyze our problem in the example is the xy coordinate, and the coordinate is fixed at one origin, at one single reference point, and doesn't move. But to analyze some problem, when a moving object is travel around along the plane, on the plane, and the normal and tangential coordinate is one useful coordinate. In this page, when I describe the concept of the normal tangential coordinate, after completing this slide, we will see, we can think about what is the advantage of this coordinate. And what I want to tell you by now is, in some applications such as a mobile robot or automobiles motion that travel on a plane, sometimes we don't care where is the robot or where is the car as respect to the global coordinate. But we just want to control the robot at that position, control the velocity along its longitudinal or lateral direction of that mobile robot or of that car. The NT coordinate is useful in that application. When I try to analyze the dynamics of a drifting vehicle, an automobile may have a wheel when it's here. An automobile may have a four wheel like here, and we can attach one frame that attached to the center of gravity of that automobile. We have the longitudinal direction and the lateral direction of the coordinate on an automobile. But when the automobile travel, for example, we have a curve. The curve should lie on the center of gravity. Sometimes the vehicle is drifting along the curve, and the velocity vector is not lie on the x and y of the vehicle. We are going to introduce another coordinate called the NT coordinate. We have the t direction and the n direction. The t direction is the direction of the velocity vector, and the n direction is the direction that's normal to the t direction. With this, the velocity will only be in the t direction, and we're not gonna have the velocity in the n direction because it's normal to velocity. And with this description of the coordinate and with this property that it doesn't have the velocity in the n direction, we can take some benefit from this coordinate. So what does it mean by velocity vector is just only has the component in the t direction. We are going back to the schematic here. Before this, we may have the x and y coordinate that attach to a reference frame. But the nt coordinate is a moving coordinate that attached to a particle. The 0, 0 of the nt coordinate is on that particle, and the t axis, t direction, is the direction of the velocity of that particle. When time equal to 0, the particle is at point A, and when time passes, it shifts the position to the A prime. The velocity at A is the direction that tangent to the curve at point A. The velocity at the point A prime have the direction that tangent to the curve at point A prime. And the t direction is in the direction of vector. The t prime also has the direction to the vector v prime. And the unit vector, before this, for the x and y coordinate, we have the unit vector I, unit vector j, right? For the nt coordinate, the unit vector that belong to the t direction is described by the e with a cap and in t direction. As I mentioned, we have the t direction and we have another direction that normal, that perpendicular to the t direction. The axis is the n axis, and the unit vector of the n axis is en with a cap. And if you consider a particle moving from a point A to A prime, from a point A to A prime, with a very small distance, from A to A prime, the distance is estimated by the radius of curvature. The radius of curvature multiplied by the angle at the instantaneous center. In a very short period of time, the distance ds is equal to the radius rho multiplied by the angle, the very small angle, delta beta. The rho multiplied by the delta beta. This is at a in a very short period of time. For the nt coordinate, we said that we have only the velocity in the tangent direction. Why? Because if we talk about the very short distance vector, here the magnitude of the short distance is rho dB, and the direction of the rho dB, yeah, is along the velocity vector or along the t axis. So the velocity can be the first time derivative of the small displacement, and yeah, we can write down this as a dB by dt, and please note that in a very short period of time, we still ignore the change in the direction of the t. We still neglect the change in the direction of the t. But we're gonna write the velocity vector as the product of the radius of curvature multiplied by the angular speed. And in the direction of the tangent axis. And the radius of curvature multiplied by the beta dot or the angular speed is equal to the magnitude of the velocity. So velocity vector is the magnitude of velocity multiplied by the unit vector in the tangent direction. And the magnitude of the velocity can also be written in the terms of the product of the radius of curvature and the rate of change in the angle or the angular velocity. Angular velocity. So angular velocity of the what is the angular velocity? Angular velocity of how the n axis change its orientation. Angular velocity of maybe n, how the n change the orientation, or the unit vector of n axis change its orientation. It also applicable to the angular velocity of t or the unit vector also. All of these share the same angular velocity. And yeah, finally, to sum up, the nt coordinate is composed from the information of the speed and the direction of the speed. Now, this is just only a velocity. We still don't know how important of this coordinate when we see only the simple composition of the velocity to the unit vector t. But if we try to obtain the acceleration is the time derivative of the velocity. So is equal to the d by dt of the low beta dot and unit vector. D by dt of this will be the acceleration. So how can we obtain the d by dt of this? We need to obtain the d by dt of the first parenthesis inside of the low beta dot and keep the unit vector, and then plus by the low beta dot and multiply by the d by dt of the unit vector. And yeah, to obtain the time derivative of low beta dot, we're gonna have the low dot beta dot plus low beta dot dot in the direction of the tangent axis. And for the second term, we have the low beta dot and the d by dt of the unit vector. I want you to see this small diagram. I want you to see this small diagram. In the original point, at point A, the velocity vector lies on the unit vector et. And when it changes the position from A to A prime, the unit vector just change the direction with a small angle beta. It changed the direction with the angle d beta from this orientation to this orientation with a small angle. So the difference between the unit vector, the difference between the vector of the unit vector is described by the d of the unit vector. The unit vector has the magnitude. The magnitude of the unit vector is equal to 1, right? The magnitude of the unit vector is equal to 1. So the radius of this, the radius is equal to 1. And the angle is delta beta. So angle multiplied by the radius will be the part of the circumference. So from this, the d of the unit vector is equal to the radius 1 multiplied by the d beta. And here is the magnitude of the d of the unit vector. What is the direction of the difference between the unit vector? What is the direction? What is the meaning of this direction? If you see here, from here, the first unit vector and this is the second unit vector. It seems like the direction of the different DE is likely to go in the same direction with the unit vector of the normal direction by the geometry. You see this? The direction of the n is going to this direction, and the change in the direction of the tangential unit vector is assumed to be in the direction of the normal direction. And the magnitude of the dE is equal to d beta. So if we consider this again, it seems like dE is equal to 1 multiplied by d beta. So this will be d beta by dt with the direction to the normal direction, En. So if we write the acceleration, is equal to the low dot, beta dot, plus low, beta dot dot in the tangent direction, plus the low beta dot square in the normal direction. And this is the acceleration in the tangential direction. And this is the direction in the normal direction. I think you may familiar with.
Why is it in the normal direction again? I didn't quite get it.
โอเค
ทำไมมันถึงเป็น n en นะครับ
โอเคwait a second. Maybe let's see this picture. Maybe let's see this picture. We have tangent and normal, and we have, when the time pass, we have the new tangent and the new normal. And if you see this and this, if I try to bring this, you need to imagine, okay? If I try to bring this to this position, just slide the vector of t palm to this position, and the length of the unit vector is 1. The length of unit vector is 1. It seems like the delta maybe one more time. We have a circle like here. And we have the unit vector of the ET, and we have the perpendicular axis with the unit vector En at this point. if we shift to this point, the ET prime and the EN prime will be like this. I think until here, you can accept about what you can understand what I write here. But after this, try to imagine that we slide this component of vector to here. Why we need to slide it to here? Why we need to slide it to here? Because we want to write the unit vector ET, which is the original one, and ET prime, which is the unit vector of the tangent after it moves, and the delta of the ET will be this. The delta of the ET will be this. And I don't know why, but by the graphical method, if we precisely draw the direction of the unit vector, it seems like the direction here, the direction of the distance, the direction of the difference between the vector will normal, but I think it makes wait. Okay. From this picture, if the angle is d beta, the small angle d beta, okay? The angle d beta will be the angle between the tangential vector also. And the radius are the same. And the distance or the difference between the unit vector here, when the angle is very, very small, can you imagine when the angle is very small, this distance almost perpendicular to the direction of the unit vector. If the angle d beta is very small, the difference between E, T, and ET prime, if the angle is very small, it's almost the same line between the it almost the same line between the ET and ET prime. And the distance here, is perpendicular to the radius. It seems like the circumference is perpendicular to the radius. And what is the axis that perpendicular to the ET, the unit vector of ET? The EN is the axis that perpendicular to the ET. So I think this is the explanation why finally the dip of the DE is going into the direction of the EN. And the magnitude is described by the angle in the center, because the magnitude of the DET is the angle multiplied by the radius, but the unit vector has the magnitude of 1, so the radius is equal to 1. Is better? It's still unclear? Can you hear me?
Yes.
It's okay. We need to imagine that. When in the original state, the unit vector is in the direction of the velocity. After the time pass, the velocity change the direction. The velocity change the direction. And we need to find the difference of the vector. We need to find the difference of the vector. And now you see this angle, right? No, the angle is not a right angle. Now the angle is not a right angle. And these two vectors have the different in direction. But if the time difference is very small, and this angle is very small, these two lines almost being the same line from a big difference. When the time is very small, the line is almost being the same line. And the angle here will almost be the right angle, 90 degrees. Can you accept this assumption? When we have a big angle at the center, the angle here and the angle here will less than 90 degrees. But when this angle is very, very small, it seems like you have two lines almost in the same position. And the angle here is almost 90 degrees. Can you accept this assumption?
Yes.
Yeah, but what is the thing that have 90 degree different in angle with the t direction? That is the n direction. Yeah, this is explanation for this.
Teacher?
Hmm?
So when the time is very small, the derivative of the unit vector will become perpendicular to itself, right?
Yes.
Okay, thank you.
Yeah, the difference of the unit vector will perpendicular to itself. Yeah.
Okay, so that's why our ET becomes EN.
Yes.
Thank you.
Yeah, something like that. You may need to like check this explanation in the textbook again and try to read about normal tangential coordinate from like maybe external source. It need time to understand. Yeah. But finally, what we get is the tangential acceleration and the normal acceleration. You may familiar with the normal acceleration when you talk about something travel in the curve. You may know that the acceleration that go to the center may equal to the v square per r, or equal to omega square r. Do you remember some simple relationship like this?
Yes.
The acceleration to the center of the motion will equal to v square per r, or equal to omega square r. This case is true for motion of a disk. When the radius doesn't change, when the disk move with omega and has the radius r, the velocity at this v is equal to omega r. And yes, in this case, the acceleration to the center will be omega square r, or v square per r. We studied this in physics 1, but in this case, we are not consider the change in the radius or in the normal direction to the velocity. The disk has constant radius, but for today, when we combine the effect of the change in the tangential velocity and the change in the radius, we may have the new formulation. Hey, it's wrong. I mean, you should forget this. No. Because the disk that I explained, we should use the r and the theta coordinate in the next week. If we use the r and theta coordinate, we consider the change in the radius. But in our case for today, we have the velocity only in the tangential direction, and we don't have the velocity in the normal direction. So it means the change of the radius shouldn't be like considered. But okay, to simplify, this is
อาจารย์ครับ
messy. ครับ
ไอตัวที่อาจารย์เขียนมุมซ้าย DE เท่ากับ DB อ่ะอาจารย์เอามาใส่แต่ว่า คือตัว EN ที่เพิ่มเข้ามามันคือเอาไว้บอกทิศหรือว่ามันเอาไว้บอกอะไรนะครับที่มันเพิ่มเข้ามา
โอเคเดี๋ยวนะแป๊บนึงนะ
จากแบบมุมบนซ้ายที่อาจารย์พิสูจน์มันเขียนว่า DET เท่ากับ DB ใช่ไหมครับแต่ว่าแบบ EN ที่เพิ่มเข้ามา
magnitude ของมันตรงนี้ผมเข้าใจละจริงๆตรงเนี้ยมันคือ in this sorry this is wrong what I write here is just the magnitude. If you need to complete it, you need to put the direction. It should be like this. So the magnitude of the DE is equal to the radius 1 multiplied by the angle delta beta, the magnitude. But the direction is perpendicular to the tangential. So it should be in the normal direction. So this is correct. So yeah, is why we have the change in the magnitude and the EN as the direction. Still unclear?
Yeah.
Yeah, but to summarize, we have the velocity, and the velocity will be only in the tangential direction. And the velocity is equal to the radius of curvature multiplied by the rate of change of the angle in the center, rho beta dot, or you may familiar with R multiplied by omega equal to the magnitude of the velocity. Is almost the same, is similar. And the direction of the velocity just only in the direction of the tangent. We don't have the velocity in the normal direction. We have the velocity only in the tangential direction. And the acceleration is the d by dt of the velocity will equal to the dip of the first thing here. It's gonna be rho dot beta dot plus rho beta dot dot in the direction of the ET in the first term. And in the second term, we will have the rho beta dot multiplied by the d by dt of the unit vector. And if we talk about the unit vector, in the beginning, the unit vector t go into one direction, that is the velocity direction. After the time pass, the unit vector change its direction. And how much it changed in the direction? It changed the direction by the small angle beta. So if we want to find this distance is the vector d of the unit vector, is the difference of the unit vector. It's also a vector. You can consider it as a delta of the unit vector, but in a very short period of time, from the delta, we use the d. The angle in the center, instead of the delta beta, we also use the d beta. And what is the magnitude of this? What is the magnitude of this? The magnitude is equal to the angle multiplied by the radius, but the unit vector has the radius, the unit vector has the length. The unit vector has the length of 1. So the radius equal to 1 and the angle equal to d beta. So the magnitude of the magnitude of the delta is equal to d beta multiplied by 1. If you consider only the magnitude, it's just the small angle multiplied by the length of the unit vector. But if you consider the direction also, the direction of this, if d beta is very small, this angle can be assumed as a right angle 90 degrees. When this is 90 degrees, the direction of the unit vector can be assumed to be the direction that perpendicular to the unit vector et, which is the direction of the unit vector en. So here, the magnitude is dB delta beta multiplied by 1 with the direction of en. And if we want to obtain the d by dt of the difference d by dt of the different will equal to dB by dt of the en in the direction of en. And yeah, it'd be the beta dot in the direction of en to here. So in this term, we're gonna get the low beta dot square in the direction of en. Yeah, please try to understand this. Maybe the textbook has the extensive explanation, but yeah, to derive this, you need to try to accept the assumption. And if you cannot remember the formulation here, if you cannot remember the formulation here, you can begin from this and do the differentiation. And finally, the acceleration, we have the acceleration in the normal direction and the tangential direction. I think we don't have much time, and for today, we can end with this example, but for this, we will continue on next week, but try to complete this example by today together. Wait a second. Okay, there is a car, a race car, and it's traveling with a speed. It's traveling with a speed, and it drives along a straightway, and it enter the cornering. It enter the cornering, and if we just consider the acceleration in the direction of travel, it changed the speed from 250 km per hour to just 200 km per hour. So from the point A to point C, with the distance of 150 meter plus, it changed the speed from the higher speed to the lower speed in deceleration. And in the problem, we need to compute the total acceleration when it passed the point B. So what we need to imagine is, yeah, the car is deceleration. So it should have the acceleration in the, how to say, in the direction of the motion, the direction of the velocity. It should have the acceleration in the direction of the tangent. And on the straight line at point A, it should have only the acceleration in this direction. But when it passed through the point B, it entered the cornering. It should have another component of the acceleration to make the car run in the curvature, in the curved part. So we know that the acceleration in the normal direction, is just like it's just v square divided by rho. Yeah, the normal acceleration, or the A in the normal direction is equal to the radius of curvature multiplied by the angular velocity square. But we know that the velocity or the speed, the magnitude of the velocity or the speed is equal to the rho beta dot. The speed is equal to the radius multiplied by the angular velocity, right? So it's not wrong to write the normal acceleration in the terms of velocity square divided by the radius of curvature, because the rho beta dot square divided by rho is equal to the rho beta dot square. So yeah, in this problem, at the point B, if we put the NT
ขอดูหน้าเมื่อกี้อีกที
coordinate
ได้ไหมครับ
ตรงนี้ใช่ไหมครับ
ครับครับ
Okay, we know that the speed is equal to the radius multiplied by the angular velocity, and you already derived the acceleration in the normal direction. The acceleration in the normal direction is equal to radius of curvature multiplied by the square of the angular velocity. What you may familiar with from the physics one, maybe V equal to R omega. The acceleration to the center of the rotation is equal to omega square R. This may be what you're familiar with, and is similar to our NT coordinate. But what I'm going to do is, how can we relate the normal acceleration to the velocity, to the speed or the magnitude of the velocity? if we don't want to talk about the angular velocity, how can we do that? So from this relationship, we know that the beta dot or the angular speed is equal to the tangential speed divided by the radius. So if you substitute this information to here, an or the normal acceleration will equal to the radius of curvature multiplied by the tangent speed divided by the radius of curvature and take the square. And it equal to v square per rho. For the normal acceleration at any time, the normal acceleration can be written in the terms of the angular velocity, beta dot. Also, it can write in the terms of the speed divided by the radius of curvature. Maybe from the previous physics class, you may be familiar with the acceleration to maybe the centrifugal acceleration or the acceleration to the center of the rotation is equal to v square per r. You may be familiar with this. Yeah, but for this case, now I think for this is for constant omega. Yes, I think now it's matched between our two cases. For a constant angular velocity, you can compute the velocity of a particle on a dish. You have a dish that rotates with omega, and you know the radius, and the velocity vector is equal to the omega multiplied by r with the direction of the tangential to the disk circumference. And the object, although the omega is constant and the velocity doesn't change its magnitude, the object here needs to have the acceleration to the center direction because it needs to travel on a curve. So the acceleration to the center is equal to the omega square r or v square per r. But in this case, constant omega and constant speed. In our case, for the nt coordinate, if we consider only the change, the acceleration in the center direction is the normal acceleration. But if we consider the change in the speed, or the acceleration in the tangential direction, we also can talk about this. So in your previous study from the previous course, the physics course, you talk about the relationship between the angular velocity and the radial acceleration in the terms of the omega and the v. But for the nt coordinate, for the normal direction, we have the same relationship. but we add the case, the more complex case, when we change the speed in the tangential direction also. Yeah. So now the normal acceleration is the v square divided by the radius of curvature. So what the problem gives, we know the speed at point A. The speed at point A is equal to 250 kilometers per hour. And the speed at point C, here, after deceleration, the speed reduced to 200 kilometers per hour. The change of the speed happened in the distance of 150 plus 150 or 300 meters. The change of the speed happened in this distance, and we need to compute the total acceleration. They want the magnitude. What we familiar with is what we can use from the rectilinear motion is to obtain the tangential acceleration. The tangential acceleration is the change of the magnitude of the speed divided by the time. But in this problem, they didn't give the information of the time. So why not we try to relate the speed to the distance and the distance to the time. So by this relationship, this is velocity. We can compose the relationship between like acceleration, displacement, and the speed. Right? A tangential multiplied by the ds is equal to v dv. And we are going to put the integral on both sides because the velocity is not constant. And the integration need to do from the distance point A, distance s is 0. And it decelerates to the point C. The distance is 300 meters. And the velocity change from the velocity at point A. The velocity at point A is equal to 250 kilometers per hour. 250 kilometers per hour multiplied by 1,000 meters per 1 kilometer and multiplied by 1 hour equal to 3,600 seconds, which means that 250 kilometers per hour, it should be divided by 3.6 so that we can get the meter per second. We need to divide by 3.6. So the velocity, the speed at point A is 250 divided by 3.6. And at point B, the velocity or the speed is 200 divided by 3.6. This is the limit of the integration. So okay, they said that they reduce the speed at a uniform rate. What does it mean by this sentence? Reduce the speed at a uniform rate. So it means that the tangential acceleration is constant, right? Because they reduce the speed at a uniform rate. So in this case, the AT is a constant, but we still don't know the value of the constant. But we can bring it out from the integration. So we can write down AT and the integration of ds from 0 to 300 of the distance. And on the right hand side, the integration of v dv is v squared per 2. And the limit of the integration is from 250 divided by 3.6 and 200 divided by 3.6. And the tangential acceleration multiplied by 300 subtract by 0 is equal to 1/2 of the 200 divided by 3/6 square subtract by the 250 divided by 3/6 square. And we can compute the tangential acceleration by calculator. And one thing we need to observe is that I'm not gonna ask you the value of AT. I'm gonna give you the value by the calculator. But do you think what is the sign? What is the direction of AT? Is positive or negative?
negative.
Yes, because in this case, the car is decelerate. And when we check here, the second term is bigger than the first term. So the AT is a negative value. This is the tangential acceleration. To compute the normal acceleration at point B, you need to know the speed, the tangential speed at point B. You need to know V in order to compute the AN. But now you know the uniform acceleration, right? So we can do the same, like the integration also. Yeah, we need to do the integration again, but for this time, the integration of the A tangential by ds is equal to the integration of v dv. We should focus that here is at point B. Okay, so from point A to point B, we need to integrate the acceleration from the distance 0 to 150 at point B. The distance is 150. And the speed that we don't know. We know that the initial speed at point A is 250 divided by 3.6. But we don't know what is the speed at point B. We still don't know the speed at point B. Now we already know that the AT, the tangential acceleration, is a constant, and the integral, we have the AT and multiply by the change in the distance on the left-hand side. And for the right-hand side, we have the v squared divided by 2. And the limit of the integral from 250 divided by 3.6 and the unknown velocity or the speed at the point B. And we know the AT, right? And we know the limit of the integration, but we need to obtain the velocity at point B. So you may need to take your time to use the calculator and confirm that the speed at point B equal to, I didn't compute VB, but I compute VB square. The VB square, from my computation, I got 3,954. And why I compute the VB square instead of VB? Because the normal acceleration is equal to the normal acceleration at point B is equal to the speed at point B square divided by the radius of curvature. So you're gonna have 3954.3 divided by the radius of curvature. The radius of curvature is 500 meter. And then you're gonna have the normal acceleration. And before this, we know the tangential acceleration. And the total acceleration vector at point B is equal to the tangential acceleration in the t direction and the normal direction in the n direction. If you need to answer the acceleration vector, you can write the magnitude of the tangential acceleration and the magnitude of the normal acceleration multiplied by the unit vector. But if we need to know the magnitude of the acceleration, you can take it from the square root of the square. Yes, so I think it's enough for us today. It's a long day, and you may need to review the concept first before we jump into the more complicated problem here.
อาจารย์ครับAT อะครับมัน constant ตลอดเส้นทางเลยใช่ไหมครับ
Yes, because from the problem and the way we try to derive the solution, we derive it based on this statement. The statement that he reduced his speed at a uniform rate. Reduce a speed at a uniform rate means the rate of change of the speed is constant. So the tangential acceleration is constant at point A, B, and C. Yep. Okay, still have any question?
อาจารย์กลับไปสไลด์หน้า normal and tangent coordinate อีกรอบได้ไหมครับ
นะครับเดี๋ยวนะ
ไอบรรทัดที่3อะครับ
ครับ
อาจารย์ให้ et แล้วไอจุด et เนี่ยให้เป็น0ใช่ไหมครับ
ใช่ใช่ใช่
ทำไมนี้เป็น0ล่ะครับ
ตรงนี้มันจริง ๆแบบ
มันคืออันเดียวกันกับอันข้างล่างที่เป็น
ใช่ใช่ใช่จริงๆมันอันเดียวกันกับข้างล่างเว้ย
อ๋อ
แต่ว่ามันตรงนี้เนี่ย ผมเจอบั๊กเหมือนกันว่ะคือตรงนี้ผมพยายามจะ compose ไอตัว velocity vector มาจากไอตัว definition ของตัว displacement ซึ่งจริงๆแล้วมันต้องดิฟทั้งตัวข้างหน้าแล้วก็ดิฟตัวdirection
ครับ
แต่จริงๆถ้าไปดูใน textbook จริงๆมันตัดไอ้ point นี้ทิ้งไปเลยใน textbook มันจะยกมาว่าเป็น v เท่ากับ low beta dot ของตัว unit vector ใน tangential เลย
อ๋อ
ตรงนี้จริงๆผมก็ยังงงเหมือนกันว่าเฮ้ยไอตัวข้างบนเนี่ยผมต้องทำให้มัน estimate เป็น zero เพื่อจริงๆถ้าจะให้พูดใหม่ตรงนี้นะขอไม่รู้ว่ายังอยู่กันครบไหมแต่ว่าถ้าจะให้ผมกลับมาอธิบายตรงนี้ใหม่อีกทีผมพยายามจะบอกว่าจริงๆมันคงไม่ใช่ estimate เป็น0ที่มันคงไม่ estimate เป็น0ที่ unit vector แต่ว่าตัวที่มันเป็น0ของเทอมนี้ควรจะเป็น rho multiply by d beta มากกว่าใน derivation ของเรามันจะมีหลายจุดที่มันเป็น d beta dy by dt แต่ไอการที่มันเป็น d beta dy by dt มันเป็น diff by diff ซึ่งมันเป็นส่วนเล็กๆมาหารกันแล้วมันได้ค่าออกมาแต่ว่าจุดไหนที่มันเป็น multiply by d เฉยๆก็คือมันคูณด้วยสิ่งที่มันเล็กมากๆมันจะ estimate เป็น zero งงไหม
เข้าใจแล้วครับ
ครับเพราะฉะนั้นถ้ากลับมาอธิบายตรงนี้อีกทีนึงส่วนที่ estimate เป็น zero ไม่ใช่ตัวการเปลี่ยนแปลงของ unit vector เพราะการเปลี่ยนแปลงของ unit vector มีค่าเป็น direction ออกมาเหมือนที่เราอธิบายกันยืดยาวแต่ในเทอมนี้ส่วนที่เป็น0จริงๆคือส่วนที่เป็น d beta มาคูณอยู่ครับ
ทำไมข้างล่างมันมีค่า
ข้างล่างคือตัวไหนนะบรรทัดไหนดี
ตัว A อะครับ ที่เป็น E ที่เราไปดิฟได้ที่เราไปดิฟได้อ๋อมันก็คือเทียบทีมเหมือนกันใช่ไหมครับ
ใช่ถ้ามันเทียบทีถ้ามันเป็น d beta by dt มันจะมีค่าแต่ถ้ามันเป็น d beta มาคูณเฉยๆมันเหมือนเอา0มาคูณแต่ถ้าเป็น d beta by dt มันเหมือนเอา0ส่วน0มาคูณ
เข้าใจครับก็คือถ้าเป็น d beta อย่างเดียวมันเหมือน estimate เป็น0ไปแล้วแต่ว่าถ้าเทียบทีด้วยมันคือเหมือนดิฟ
ใช่ประมาณนั้น
อาจารย์ครับแล้วทำไมพวกตัว ij มันได้0เหรอครับ
หมายถึงยังไงนะ
ij มันได้0ใช่ไหมฮะ
ij หมายถึง diff i diff j ใช่ไหม
ใช่ครับ
diff i diff j มันเป็น0เพราะว่า i กับ j มันไม่เปลี่ยนทิศทางแต่ถ้าเป็น diff e t กับ diff en มันไม่เป็น0เพราะว่า e กับ t มันมีการเปลี่ยนทิศทางด้วย
อ๋อมันเปลี่ยนไปเรื่อยๆใช่ไหม ET
ใช่มันมีการเปลี่ยน direction ไปเรื่อยๆครับ
อ๋อเข้าใจแล้วครับ
ทีนี้ผมฝากเราไปคิดเล่นๆอีกนิดนึงแล้วกันหน้านี้มันมีหลายที่ที่เราเถียงกันว่าเฮ้ยทำไม d ของ unit vector e เนี่ยถึงได้มาอยู่ในทิศของ normal direction ผมฝากเราไปคิดเล่นๆเผื่อแล้วกันว่าเฮ้ยแล้วถ้าดิฟของ normal direction สุดท้ายมันจะไปใน unit vector ไหนฝากไปคิดเล่น
แทนเจนต์มาครับ
ๆเป็น tangent แต่เป็นบวกหรือเป็นลบ tangent
โจทย์คืออะไรนะครับขออีกทีหนึ่ง
บวกครับบวก
เราดิฟ tangent ดิฟ unit vector ของ tangent แล้วมันไปตกอยู่ใน normal direction แล้วถ้าเกิดเราดิฟ normal direction
เราจะได้อะไรอย่างนั้นเหรอครับ
ใช่เราจะได้อะไร เมื่อกี้มีเพื่อนฮินต์มาว่ามันอยู่ใน tangent direction ผมบอกว่ามันถูกว่ามันอยู่ใน tangent direction แต่ถามว่ามันเป็นบวกหรือเป็นลบของ tangent
น่าจะเป็นลบหรือเปล่ามันใจเลยเราว่าเป็นลบ
ดูด้วยตาเป็นลบใช่ถูกลองไปค่อยๆดูอีกนิดนึงพวกเรามี textbook กันไหม
ที่หน้าปกเป็นอะไรนะ
ของเมอร์เรียมจริงๆมันเป็น edition ไหนก็ได้เป็น textbook ของเมอร์เรียมก็ผมมีเป็น hard copy ของเวอร์ชั่นเก่าแล้วแต่จริงๆผมก็ไปหาโหลดในเน็ตมาเป็นของเวอร์ชั่นที่มันใหม่นะแต่คือจริงๆมันมีปล่อยให้โหลดอยู่เหมือนกันถ้าขี้เกียจไปหา
มีที่เป็น 7 edition นะครับ
ก็น่าจะใช้ได้ลองไปอ่านตรง explanation ใน textbook ดูก่อนครับโอเคขอบคุณครับ
ขอบคุณครับอาจารย์
ครับ
ขอบคุณครับ
ครับ